All right, let's talk CUET. I know that D-block section can feel like a total maze, right? But what if I told you there's just one core secret that unlocks pretty much every question they can throw at you? Yeah, together, we're gonna crack that code. Okay, let's just dive right in with a classic trap question. Seriously, this is the kind of thing examiners love. Look at this. How on earth is zirconium from period 5 almost the exact same size as hafnium, which is right below it in period 6? I mean, logically, hafnium should be way bigger, right? It's got a whole extra shell of electrons. This stumps so many students. But in the next few minutes, I'm going to show you why the answer is actually super simple, and it all comes back to one hitting superpower of the D block. So, to solve that puzzle, and honestly, to just dominate any question on this topic, we can't just memorize a bunch of random facts. That's a losing game. We need to get to the root cause, the one fundamental reason these metals behave the way they do. It's actually really simple, but trust me, it changes everything. And here it is. This is the big secret. You ready? Most elements, they're like a person only using their hands to do work. That's their outermost electrons. But transition metals? Oh no. They use both their hands, the outer S electrons, and their elbows, the inner D electrons, to get involved in bonding. I mean, just think about it, right? Using both your hands and your elbows gives you a way stronger grip. And that's why their metallic bonds are so incredibly strong. And I'm telling you, this one fact, this one idea, it explains almost everything else we're about to talk about. Okay, so we've got these super strong bonds. So what? Well, what's the result? It directly explains all those physical properties that the CUET exam loves to ask about. Let's connect the dots. Just look at this comparison. It's night and day, right? Because of that extra S and D electron glue holding everything together, the atoms are packed in super tightly, and bam, that's your high density. Trying to break those bonds, it takes a ton of force. That's where their hardness comes from. And trying to pull them apart with heat to melt them, well, you're going to need a crazy amount of energy, which explains those sky-high melting points. See, it all comes back to that one core secret. It's all connected. And if you need more proof, here it is. This fancy term, enthalpy of atomization, all it really means is the amount of energy you need to literally rip 1 mole of the metal apart into individual, separate, gaseous atoms. For transition metals, this number is just huge. And why? You guessed it, because you're fighting against that powerful double grip from both the S and the D electrons. It takes a massive amount of energy to pull those atoms apart one by one. Okay, quick attention reset. Listen up. Examiners, they know the rules. But what they love to do, where they really get you, is testing the exceptions. This is how they separate the students who just memorized a textbook from the students who actually get it. Let's make sure you are in that second group, for sure. So let's talk about mercury. Why is it a liquid? I mean, it's a transition metal. It should be tough, right? Well, here's the deal. Its d orbitals are completely full. They're stable, they're happy, and they just don't want to play. They don't want to get involved. So with no help from the d electrons, you get really weak metallic bonds, and boom, you've got a liquid. Now, this is important. I want you to actually pause for a second and think about this. Why does being full and stable lead to weak bonds? The answer is bonding is all about achieving stability. If an orbital is already in its most stable state, it has almost zero reason to form strong bonds with its neighbors. It's perfectly content all by itself. Okay, that was the warm-up. Now for the concept that really, and I mean really, separates the top 1% from everyone else. I need your full focus right here. This is where we solve that mystery we started with. All right, we all know the basic rule from way back, right? As you move from left to right across a period, you're adding more protons, more positive charge to the nucleus. It's like adding more magnets. This stronger pull sucks the electron shells in tighter, and so the atomic size gradually decreases. Simple enough, right? But in the D block, this simple rule doesn't just bend, it completely breaks. In a massive way. Okay, it's time to face the final boss of this topic, the lanthanoid contraction. This is a classic exam trap. It's a favorite of paper setters everywhere. But after the next minute or so, you're going to be the one who sees the trap from a mile away. So, what is it? The lanthanoid contraction is this really unexpected decrease in the size of atoms that happens right after you go through the lanthanide series. And the entire reason, the whole thing, comes down to one phrase you absolutely have to burn into your brain: the poor shielding effect of the 4f electrons. But okay, what does shielding even mean? And why are these 4f electrons so terrible at it? Let's just walk through it step by step. So before you get to the 5D transition series, that's where our friend hafnium lives,
The 4f orbitals are getting filled up. Now that means you're adding 14 protons to the nucleus. That's a huge increase in positive charge. But here's the problem. The 4f electrons that are also being added are just horrible at their job. Their job is to shield the outermost electrons from that growing nuclear charge, and they're terrible at it. So what's the result? The nucleus has a much stronger effective pull than it's supposed to have, and it just yanks those outer electrons in super tight, literally contracting the atom.
And this right here is the answer to our very first question. We've come full circle. Just look at the graph. You would absolutely expect hafnium to be way bigger than zirconium. But that lanthanoid contraction, that massive squeeze from those poorly shielding 4f electrons, it shrinks hafnium down so much that it ends up being nearly identical in size to zirconium, 159 picometers versus 160. It's incredible. Mystery solved.
Okay, you get the theory, that's great, but can you apply it under pressure? Let's find out. Time for a quick QET style challenge, just like the real thing. Get ready.
All right, look closely at the options. Which one of these pairs has surprisingly similar chemical properties, specifically because their sizes are so alike? Is it A, scandium and yttrium, B, zinc and mercury, or C, zirconium and hafnium? I'm giving you 5 seconds on the clock. 5, 4, 3, 2, 1, lock it in. And the correct answer is, of course, C, zirconium and hafnium. And here is the pro tip I want you to take into the exam hole. In chemistry, to a huge extent, size dictates properties. Because the lanthanoid contraction makes their atomic radii nearly identical, their chemical properties are also strikingly similar. Write this down if you have to. Similar size means similar chemistry. That's a total game changer. All right, let's bring it all home. We've covered the core secret. We've connected it to the physical properties. We've looked at the big exception, and we've dismantled the #1 trap. So here are the absolute must-know rank-boosting takeaways you need to lock in right now. Let's lock this in quickfire style. The why? It's that S and D electron double grip, creating super strong bonds. The result? High melting points, high density, real hardness. The trap you'll never fall for again? The lanthanoid contraction, making those 4D and 5D series elements, like our friends zirconium and hafnium, nearly identical in size. And the exception? You gotta remember mercury and its weak bonds from those full D orbitals. Master these 4 points, and you have officially cracked the D-block code for CUET.
So, we've officially closed the loop. You now know exactly why zirconium and hafnium are almost the same size. But that leads to an even bigger question, doesn't it? If their size is the same, what other properties of zirconium and hafnium might be almost identical as a result? Think about things like their ionization energy or their chemical reactivity. That's the next level of understanding. Think about that. Keep digging deeper, and I'll see you in the next explainer.